Okay, good morning, everyone. I think we can begin. We've got a good number of people in already. Thank you, everyone, for joining today, and welcome to the inaugural webinar by the Cambodia Green Building Council for 2025. Today, we will be running through an introduction to air conditioning design, which will be presented by Blue Snow Energy Corporation Limited. Just a quick introduction. My name is Ashwin. I'm the Executive Director of Green RE and also the Treasurer for the Cambodia Green Building Council. I will act as the MC for today. We will begin with a quick introduction by Mr. Chia Boon Siang, who is the President of the Cambodia Green Building Council, after which I will pass the floor over to Blue Snow Energy. Mr. Bernard, who is heading Blue Snow Energy, is also the Vice President of the Cambodia Green Building Council. Just a bit of housekeeping. I hope please everyone keep your microphones muted. We will have a Q&A after the presentations. Put your questions down in the chat portion of the platform. And if there's any need for further clarification to any of your questions, we will ask you to unmute and explain your question further. So without any further ado, I will now pass the floor over to Mr. Chia Boon Siang. Boon Siang, over to you.
Yeah. Yeah.
Okay.
Yeah. Good morning, everybody. Thank you, Ashwin, Bernard,
Yes.
and all the participants to join in this training. A greeting from Cambodia. My name is Boon Siang, the chairman of the Green Building Councils of Cambodia. The first start that I would like to thank for today for your time and come and join this webinar. As you know, Cambodian as a country that compared to Malaysia, we are a little bit far. It's about I think 15 or 20 years on this green, and we start these green building councils. It's very important for Cambodian to move on, since the demand in the country is now is going for the green. The policymaker also are doing, professional are also eager to learn, and the green practice are also have already been here, but not mainly Cambodia yet. So for the Cambodian Green Building Council, we more on have the vision and mission very clear that we are as a key driving force for sustainability for the so-called built environment in Cambodia. This is part of that the first our visions. We also we want to see the Cambodian community also work on the green buildings for Cambodia, and also CamGBC acts as one of the leader in the green buildings in Cambodia, and we extend to Southeast Asia in some expected to come, especially in the construction sector and the design. We needed the market demand side, and also CamGBC involved in policymakers and professional and in society at large. I mean that as of now, myself and friend are working with the policymaker in Cambodia and working on the green building policy, especially for the building green buildings. This how our mission clear on that. Also, the objective we are clear in the Cambodian Green Building Council is one, we support the government initiative. This part of that, our team already involved, work with Cambodian, we call the Council of Minister to do that, and also promote in sustainable buildings demand. So far, there is an agency like FD and other, they come to Cambodia and they promote of this. We also working on that, and research collaboration is very important. That the research and development and partnership, as what the Blue Snow always have always come in and do it, and knowledge exchange like today we do is part of that resource center that also help. So, however, Cambodia Green Building Council is one of the institutions that the leading in this sector. It means the green the buildings and the, uh, the design and also the construction sectors. However, to sustain this, I would like to inform the participant that uh, we have to find sustainability of our organization. So it means that we have to have some member for the CAMGBC. So what the benefit of the member to come once you can access to the resource? All the membership can provide to access to the resource, the training like today, and also the best practice, especially in Cambodia and the region. Cambodia is part of very good for international who are come and want to see on this green uh, uh, projects that CAMGBC is the place to take part in it. And professional development. When you become a member, you can have a professional development like today. Industrial recognitions. So far, Cambodia have many local products, but whether the green certification yet or whether recognition yet still not been seen much, but appointee is there. And also become a member of CAMTBC, you have a opportunity to collaboration with the local and also the international in the region together. Uh, and also CAMTBC support the guideline, the guidance uh, through the green building certification system and process. We work on this criteria. Uh, our expert and especially thank for Greenry always support us, and the Blue Snow also come to support in technical since we are like a little bit younger in this country, and also we make differentiate the building certification uh, for Cambodia too in any projects uh, for the investors. So, however, I think you want to know how become the membership member. Yes, we divide into the membership. Um, we have fee. As a membership, you know, the corporate member will have the per years and also partnership. Also, we have institutional partnership. Like currently, one university in Cambodia, Northern University, become our institutional partnership. And also the membership member, also individual like professional. We have many architect now come in, and also engineer, cooperative come in, and also we look for also the student uh, could be as our members. We need to keep on going. We call CBD program, continue program education. We go with that, and also the junior. So I think the list of below here are the membership fee, and I'm very happy that welcome to the participant today. You are part of us, and please join us, Cambodia. The beautiful country, and there are a lot of opportunities here for you. Thank you very much. So this is what I'm a little bit quick, but I hope you okay with that. Understand? Yes.
Thank you, Boon Tiang.
Yes.
Wow. On your
So
travel experience and
so
joining in the webinar.
so from now on, you can have a floor for your training started. Thank you very much. Yeah. Thank you.
Okay.
I'm
Thank you.
on.
Thank you.
Thank you. Thank you.
Yep.
Okay.
Okay. Just to reiterate to everyone here, the Cambodia Green Building Council is a prospective member of the World Green Building Council. And Cambodia being an ultra developing, a low income country that is developing very rapidly, are prioritizing sustainability. And the Cambodia Green Building Council aim to be front and center of the agenda for the property development and construction sector. So with that, thank you, Mr. Punchang. And I will now go to the main event for today. I'll pass the
Yeah.
floor over to Vice President Bernard from
Yeah.
Blue Snow Energy Consulting to continue with the technical portion of the webinar.
So
Over to you,
thank
Bernard.
you. Thank you. Thank you.
Thank you, Punchang. Yep.
Thank you.
Thank you, Ashwin, and thanks, Bunxiang. Hope you get on back to your journey wherever you're going. Okay, so good morning again, everyone. And welcome to today's webinar. It's titled Introduction to Air Conditioning Systems Design. My name again, Bernard Sagairaj. As Vice President of CamGBC, I'm also responsible for the technical training activities. So here I'm going to give you a short overview of what you'll be getting out of this short webinar. So today we will explore the fundamentals of designing efficient and effective air conditioning systems. And whether you are an engineer, architect, facility manager, or simply someone interested in learning more about HVAC systems or heating, ventilation, air conditioning systems, this session is designed to provide you with a foundation in the principles and practices of air conditioning design. Now, as you guys already know, air conditioning systems play a critical role in our daily lives, from keeping our homes comfortable and to ensuring optimal conditions in workplaces, hospitals, and industrial facilities. But cooling systems also consume tremendous amount of energy in buildings. So let's look at these pie charts that explain how central cooling system impacts energy consumption. So if you look at this first slide, right, a quick one. If we look at the entire world's energy consumption, buildings consume 40% of that. Now, out of that 40%, we go on to the next chart. Out of the next 40%, 60% is cooling. Of course, that will differ from the type of facility. A hospital may be 65, 70%. A mall may be 40%, but in average 60%. Now, if you dive deep into that 60%, you then see that in a central cooling environment, the chiller plant takes up 85%. And the air handling unit, which is the air side of it, takes about 15%. Okay, and all these terms I'm talking about, chiller plant, AHU, will be explained in part of the training. Now, if you then dig deeper into the chiller plant, you'll see that the chiller itself, which is like the heart of the entire cooling system, takes about 70%. And the pumps and the cooling towers will take about 30%. Again, all these terms are going to be explained in the forthcoming training. But designing these systems, right, requires a careful balance of science, engineering, and practicality. And over the next 90 minutes, our trainers, Navin Sridharan and Faris Alani, will break down the key concepts, components, and considerations that go into creating systems that are not only functional, but also energy efficient and cost effective. So a quick overview of what we're going to cover today. Number one, the basics of air conditioning. We'll start with a brief overview of how air conditioning systems work, how the refrigeration cycle, and the principles of heat transfer. Second, we look at the key components of an air conditioning systems. We'll explore the essential parts of an air conditioning system, such as compressors, evaporators, condensers, and expansion valves. All this may mean nothing to you guys for now, but later after that you'll understand, and how all the systems components work together as well. And number three, we talk about types of air conditioning systems, from split units, not much emphasis on split units, but more for central air conditioning. We will discuss the different types of systems and the applications. And number four, we look at design considerations. And this is why you guys are here. The team will dive into the factors that influence system design, including load calculation, airflow, ductwork, and energy efficiency. But not too much in detail. It's only 90 minutes. Of course, we will do that in future seminars, the more detailed ones. And finally, we'll look into global trends. We'll touch on some of the latest trends that we are seeing and what they are. So by end of this webinar, you'll have a clearer understanding of basic principles of air conditioning system design and the confidence for you to apply these concepts in your own projects. I believe there will be a short window on Q&A session at the end, but limited to 3 questions. So feel free to jot down any questions that you might have while we're going down and prepare for the end. And before we dive in, I'd like to thank all of you for taking the time for joining us today. Your participation and engagement are what makes these sessions all valuable. Okay, without further ado, let's get started on our journey into this world of air conditioning system design, and I'm excited to share this knowledge with you. I hope you find it both informative and inspiring. Okay, guys, let's begin.
Let's try again. Can you guys hear us now?
Yes, loud and
Hello?
clear.
All right. Okay. So just quick introduction myself. I'm Navin. I'm the head of engineering for Blue Snow. I've handled almost 30 green building projects. I've handled a couple of design projects. I've handled about 30 as well, energy audits. Along with me is Faris. He is the mechanical engineer at Blue Snow. He's handled a lot of about 25 energy audits as well. So we've not only seen how build systems are designed, we've seen how they aged, and in some cases we've seen how it ends. So as we get along in this, towards the later parts of the slides, I will tell you some case studies that we've come across and what some designs fail, not because the design is flawed, but rather because the designers kind of took a shortcut. So we'll get into some of that interesting bits later. So I'll let Faris lead the way for the introduction, the basics HVAC.
All right, good morning. I'm Faris Alani. So I will start this presentation with the seminar with the first one, which is what is HVAC. So this one I just quickly introduce you to what is actually HVAC stand for. It's actually stand for a heating, ventilation, and air conditioning. But in tropical climates, the terms ACMV or air conditioning and mechanical ventilation will be more often used as a cooling instead of heating, as it's very rarely used in the Asian parts. And the main objective of this HVAC system is to achieve the ideal space temperature as required by the user in the building lah. So next, I will talk about the heat transfer. This is just a basic fundamental of thermodynamics and heat transfer. Heat transfer is a process which thermal energy move from one object or material to another due to temperature difference. So there is three component of this heat transfer, and the first one is conduction. Okay, the conduction is the heat transferred through a solid material or between objects that in direct in contact, and they have different in temperature. So we have surface A and surface B. If they have a different temperature, the heat transfer will happen. And the key factor for the conduction is the thermal conductivity of the material. So the next one is convection. Convection is heat transfer through fluid. Fluid can be in gas or liquid by the movement of the fluid itself lah. So that means if objects that's in contact with movement fluids, so there will be a convection heat transfer happening there. And in convection, there's two ways the convection can happen, which is the first one is the natural convection. So there is no, okay, and the second one is the forced convection. Forced convection, that means there is additional energy input, like the spinning fan and wind movement lah. So the last one is the radiation. Radiation is actually a heat transfer through magnetic wave, or as known as the infrared radiation. So this one, it doesn't require any medium, as the heat transfer through the magnetic wave lah. The key factor for the radiation is the temperature and emissivity of the objects. So certain objects that have high in temperature without any medium, it can still transfer the heat. So if we light a lighter, even in a distance, we still can straight away feel the heat from the lights, the fire produced by the lighters. So this is some of the example in our real life lah, in application. So the first one is just a building. So in a building, the radiation, of course, the biggest heat source in the world, one of the biggest of heat source for the world is the sun. Sun, although it's like very, very far away from our Earth, and the space, there is no medium in the space, there's no air in the space, so we still can feel the heat from the sun. This is because of the radiation. And the next one is the conduction. Okay, for the building, the conduction is happening on the wall because as we know, the wall has two surface, which is the outdoor and indoor. So if the outdoor and indoor, the temperature has different. Usually outdoor is hotter, so the conduction will begins. The conduction heat transfer will begins from the outdoor to the indoor. And the next one is inside the building itself or the house, which is convection. This is can happen in two conditions. With either is a natural flow, and also if you open the fans, open the any split units, there's a wind circulation there. There's a convection happen inside the room lah, or the building. So the next one is the pot under the fire stove. So we can see that the stove, the emitting the fire, will produce a radiation, and the heat in contact with the fire, and also the bottom of the pot will have the conduction, and also the holder of the pot, because that one is a material or the solid part. And then the next one is the water inside the pot lah. So that one is moving fluids. So it's considered as the convection heat transfer. So the next one is talking about the heat load. Heat load is the amount of heat that needs to be removed to achieve the space condition required by the user. This is the term of heat load used in the HVAC. So there is two type of heat loads, which is the first one is the sensible heat, which is the heat that can causes change in temperature of a substance without changing the phase. I mean, the phase is like liquid, gas, solid. So this is the heat that required to change the temperature only. And other than sensible heats is known as dry bulb as well. The second one is the latent heat. It is the energy absorbed or released during the phase change without change the temperature. This one is just change from solid, liquid, gas without changing in the temperature of the substance. So this one is representative of the change in air moisture's content, and it's also known as the wet bulb. Okay, I will discuss all parts of the heat loads that's building related to building. Okay, the first one is the heat load by from the orientation of the building itself. So as we know, there's for building is exposed to the sunlight, and the sunlight is go from east to west. So the placement and orientation of the building is very crucial because the emittance of the sunlight is different depending on where the sun's located and the building facing the suns. So the first one, we have south-facing walls, which receive the most sunlight throughout the day. And then the second one is the east-facing wall, receive the strong morning sunlight because sunlight from the east and set in the west. So the next one is the west-facing walls, receive the intense afternoon suns, which often be the hottest. And the last one is north-facing walls, received by the least direct sunlight. So the reason the orientation will affect by the sunlight is because the walls that's facing to the sunlight. So it's highly depend on the U value as well. U value of the material used in the building. So if the walls has a lot of windows opening like glasses for glaring and lightings, so this orientation should be considered as well. The next one is the heat from inside the building itself, not really inside by the building, not the exterior parts like the sun. So for the first two is the window and wall. Window is we depend on the type of material used, and also the size depend on the U value of the material used. So window and wall can be considered as the same category. And the next one is the infiltration, which is this one is caused by the operatable openings like operatable windows and doors. The next one is occupant. This one is determined of the building occupancy, and it will affect the latent and sensible heat in the building. the last one is the equipment itself lah, inside the building. So this equipment can be the computer, the printer, and also the fridge and all that. All these electrical appliance will emit heat to the buildings, but it's mostly only sensible heat. And okay, we can see here there's a sun. Okay, this is the solar radiation. This is a window. So U value is the rate of how good is the material can absorb heat. So this is applied to the first two. And then this is the hot air from the infiltration. And then for occupants, humans, we emit moisture or can increase in the humidity as well. So but the more the density, I mean, the more the sensible heat, latent heat. The next one is the terminology, common terminology that used in HVAC. The first one is cooling and heating load or capacity. We normally use this four term, which is the first one is kilowatt of cooling. The second one is BTU, British Thermal Unit per hour, BTU per hour, or refrigerant. And the next one is refrigerant ton, which is the most commonly used. And the last one is horsepower, but this one is in common term used to describe cooling or heating load. So for unit conversion, since I mentioned that RT or refrigerant tonnage is the most used units. So for one RT equivalent to 12,000 BTU per hour, and one RT also equivalent to 3.517 kilowatt. So if we mention kilowatt, there's two type of kilowatt, which is the first kilowatt we use for electricity power consumption, and the next kilowatt, the second kilowatt is the one I mentioned here, which is for the cooling. So this is two different things. So you need to differentiate that. So in the calculation efficiency calculation of the HVAC system, the first one we use kilowatt over RT, which is the first kilowatt we use is the first kilowatt is the kilowatt by the electricity divided by the RT, which is the refrigerant ton or the cooling capacity. The formula throughout all these three is always the same, which is we comparing between the electrical use and also the heat load or the heat capacity required or being used. So the next one is coefficient of performance. This one is also widely used in most of the equipment, which we also known as the COP. The first kilowatt on top is we use as kilowatt for cooling and divided by the kilowatt for power or electricity consumption. The next one is energy efficiency ratio, EER. This one we use BTU per hour divided by kilowatt power electricity. Okay, this is one of the HVAC system, which is direct refrigerant system. This one is the most commonly used in residential and small offices, the split unit. This is the typical system that we use. And this system is mainly only used refrigerant as their medium of heat transfer. So the next one is the VRV or VRF unit. This one is a bigger capacity compared to the split unit. And it's also used refrigerant as the medium of heat transfer. And for both of these, it consists of two parts, which is outdoor unit and indoor unit. For split unit, the outdoor unit is the one with the fan outside of your house, and then the one inside your room is the indoor unit. But for the VRV, the outdoor unit is, it's all bigger. And for indoor unit, we can connect to multiple and a lot of types of indoor unit. We have wall mounted, cassette, FCU, fan coil unit, or we also known as evaporator unit. So one of these outdoor unit can supply to multiple of indoor unit. That one is for VRV, and split unit is one outdoor unit, one indoor unit. So this one is for smaller capacity. Next, okay, we dive into the system. We look closer into the system. So the basic component of this direct refrigerant system, there is four main component. which is the first one. The indoor sites consists of evaporator and fan, and the outdoor unit consists of the condenser, compressor, and expansion valve. So I will walk through how this system works. So the air that we feel produced by the aircon from the indoor unit is actually from the air indoor comes in contact with the evaporator coil, which transfer the cool refrigerant, and then it's absorbed the heat from the air and released back by the fan to the indoor unit. So that's how you feel the chill condition inside your room. Okay, what's happened to the refrigerant after the refrigerant absorb heat from the indoor unit, indoor air? So the refrigerant transfer to the hot refrigerant goes to the compressor, which here the refrigerant can in this system the refrigerant can exist in two conditions, which is gas, liquid, and it can be both mixture of gas and liquid. So before the refrigerant goes into the compressor, the refrigerant needs to be 100% in gas, because compressor cannot stand any liquid and it can harm the compressor system. So when the when the gas refrigerant goes into the compressor, it got compressed and become in high pressure and high temperature. So the temperature here is like increased that a lot compared to the when it's leave the evaporator here. So the hot pressure and hot temperatures goes through the condenser coil, where the heat from the refrigerant will be transferred to the outdoor air through the fan that will blow all the ambient air to the coil and then release all the heat to the ambient outdoor. So the refrigerant become cooler, but still in high pressure. And then it's transferred go through the dryer. This one is just to clean the gas, and actually this one at this stage is a mixture of gas and liquid. And then here at the expansion valve, the pressure will suddenly drop, and then the temperature will also drop. So then we get the cool refrigerant and goes back to the cycle, back to the evaporator coil. So that's how the cycle works lah. So the next system is the chill water system. Okay, the main difference compared to the direct refrigerant system is the chill water system use both, which is use refrigerant and also use water as the medium of heat transfer. So we have two types, which is the first one is air cooled chiller, and the second one is water cooled chiller. The main difference is obviously that is the one is cooling using the outdoor air, another one with with the water. But I will go through deeper in the next slide. Okay, this one is just example for chill water system, which is we start with the air. Okay, different from the direct refrigerant, which all the four main component is that there's only four main component and then only one loop, which is refrigerant loop. For the air, there is four main components, which is the first one is the air, which is our ambient space indoor. So the same process where the indoor air that has the heat goes to the AHU, or we call it air handling unit, and inside the AHU there is a coil as well, but instead of refrigerant, inside the coil is actually filled up with water. Now we're entering the water loop now. So the air, the heat from the air transferred to the water, and then the water will bring the heat to the chiller, which is the chiller consists of only refrigerants, where this one is not in contact so ever. So the water and refrigerant will not mix. It just pass through a coil. So this one is a coil, and then this is the coil. The refrigerant go through a coil. So this part is actually the evaporator, and then this part here is the condenser. So this is the part of the chiller lah. The chiller still consists of the four main component, which is the evaporator, compressor, condenser, and also the expansion valve. So the heat transfer from the water goes to the refrigerant, and then The refrigerant goes back to water and goes to the cooling tower. So at the cooling tower, where the water will in contact with the outdoor air, there's a fan there that will blow all the rinse water into the rinse hot water to the air and then cool down the water and come back to the chiller. So it can supply the cooler water to the chiller bag to transfer more heat from the chillers. So okay, the main the thing that you need to focus here, there is two closed loop water, and then these two closed loop fluid this closed loop water, there's two, which is the first one at the evaporator and the second one at the condenser. But different is at the condenser is actually open loop because there is opening and will contact with the air. So this one is closed loop. So whatever water stays inside, whatever inside will stay inside. So this one is still can some debris or some dust can still enter the water inside this loop from the cooling tower. Okay, the next one, this one I will tell you the difference, the main difference between the water cooled chiller and our cooled chiller. First, we need to determine where's the condenser. Where's my cursor? Okay, this is the condenser for the water cooled chiller, which is the condenser is actually connected to the open loop water, which is connected to the cooling tower. And then different from the air cool, condenser is straight away exposed to the air, and then with the help of the fan, it will cool down the coil, the water inside, the refrigerant inside the condenser. The next, okay, this is type of the indoor equipment. We have four types, which is the first one is the fan coil units, or also known as the FCU. Usually this one will be two option, which is ducted and not ducted, and there is no fresh air supplied to this unit. So the second one is air handling unit. It's ducted, and there's option where you want to for the AHU to supply the fresh air or not. So this one there's two options, which is condensed air volume configuration and also variable air volume configuration. The last one is dedicated outdoor air system, or DOS. This one is also ducted and only supply fresh air from the outside and no recirculation. So this is the main, I create the table to show the difference between all the system that I discussed just now. There's a split unit, VRV and VRF, air cooled chiller and water cooled chiller. So the main focus here is, okay, for these two, we can focus here the existence of the cooling tower. For the air cool unit, we don't need the cooling tower, but for water cool, we need the cooling tower. And for the suitable building to use this system is this for the split unit, as I mentioned, is small residency homes. VRV, VRF can be the moderate one, office, and air cool and water cool both can be used for moderate and large, but for water cooled, it's available for large capacity as well. And the average kilowatt over RT, or also known as the efficiency that we can rate the performance of the system, is 1.2 for the split units, 0.4 for VRV, and 0.9 for air cool, 0.55 for water cool. Okay, how we rate this one is actually the lower the number is the better of the performance, or the higher the efficiency of the system. So the next one is the capacity range. So split unit is between 1 to 5 tons. VRV VRF is 2 to 60 tons. And both for air cool and water cool can ranging from 20 to 2,000 tons or refrigerant RT. Okay, the next one I will pass the floor to Naveen.
Okay, now we'll be looking at towards the design protocols and the design philosophies and how to do certain systems. Let me just go back a bit. Just take note, in the efficiency rating, there's an asterisk towards the VRF and VRV. And in Cambodia, chill water systems is still considered a bit rare. They do use a lot of VRV and VRF. So in our experience in dealing with VRV and VRF systems, how you design this and how you place your systems and how you run your copper, bringing in those refrigerants to your indoor unit will play a part in how long your system maintains its efficiency. So like this efficiency here, like earlier you've seen, 0.7, this is often the efficiency you can get at the start. That means like you just build the building, you commission your system, you can get this efficiency, not an issue. But after 5 years down the line, it may be worse than an air-cooled chiller. So what kind of issues can lead to that? A VRV and VRF system actually has to be designed in a very careful manner. Case A is, for example, this right here. This is the outdoor unit. This is the indoor unit. So case A, in a rectangular building, that's a bit oblong shape. One person decides to put it on each level. The other person has done it on the top level. That means they want to keep it out a bit neat because they want to have a beautiful facade. They put all the outdoor unit on the top, and they just pull the copper pipes all the way down to the furthest end as well. Both are actually okay, but there's a caveat to this. The VRF and VRV system, most suppliers will rate it at a 100-meter max distance for the copper piping. Again, sounds like a lot. There shouldn't be an issue, especially for 3 to 4 stories building. But you will need to actually size those copper pipes if you're going for case B. Even case A, you need to properly size them. And to size these copper pipes, you will need to use those suppliers' proprietary softwares. For example, Daikin, if you're going to use a Daikin unit, you need to use their VRV system sizing software. For example, VRF Express is for Daikin. High Tech, I think, was the Hitachi's one, because you will need to actually equate the length of the copper pipes. And if you have any bends, there's an equation and calculation on what you need to do to calculate the equivalent length for a 90-degree bend or a 45-degree bend. And then only you need to size each copper pipe and how long and how thick those guys need to go to the indoor system. So what happens if you don't do it? Because in our experience, we've seen especially in even Malaysia, oftentimes when from the designer's perspective, if they're using a VRV, they just say, okay, this indoor unit of this cooling capacity sits here. The copper pipes just go straight and just goes out into the outdoor unit. They don't really size it up from that point. They leave it to the contractor. And the contractor, most of them are not really that skilled. So they just go by using the same methodology that they would often use in split unit installation. They will use the same approach for your VRV. And that will lead to certain issues. So what is the issue that actually causes the efficiency to drop? This refrigerant that flows through the pipes also carry with them oil droplets. So this oil is actually to lubricate the compressor. So this oil will be carried throughout the system. And when your system isn't designed well enough with these pipes, it can cause some pressure issues in the sense that, like Faris mentioned earlier, the compressor is also acting like a pump, pushing and pulling the refrigerant throughout the system. And the refrigerant is two-phase. So when it's pulling it back into the system, it's often trying to pull in a gas form. But these oil droplets will retain it as a liquid form. So due to the density difference, it may not be able to pull out all the oil back into the compressor. And this oil gets deposited, for example, usually this issue you'll find at the furthest distance from the outdoor unit. For example, at these rooms or these spaces, over time, maybe 4 years down the line, 5 years down the line, those rooms may end up not achieving the temperature. And due to the reduction in oil, the systems may end up, aging prematurely. Then you may need to change the VRV's outdoor unit every 7 or 8 years. It's not that this config is bad. It's just that you need to be a bit more careful and you need to be a bit more diligent in making sure that your contractors and your designers have actually sized the copper pipe. It will be as detailed as a calculation as we would normally do for a chill water piping. But again, based on our experience of seeing things, those that do case B, they don't really do that calculation. Case A also, I say the same contractor does case B and case A. Case A will be able to handle the screw up much better because your copper pipe length tends to be a little shorter. So even if you end up with a contractor who's not well versed, the design approach kind of gives it a bit of a buffer so that it can handle a bit of screw ups that happen in the copper pipe installation. So I just wanted to highlight that in case anybody was wondering why is there a 0.7 with an asterisk there, because an improper installation can lead it to lose its efficiency rather quickly, 5 years. So that's something to bear in mind when coming to BRV and BRF system. As an owner of an asset, if you're building any design, you have the right to ask them, how are you sizing your copper pipe? Show me the calculation. Whether or not they give it to you, that's a question entirely different. Okay, now let's go into space load calculation. In any design of HVAC system, the philosophy is first, you calculate how much heat is needed for the space, then you select your equipment. I have again seen in my experience, people try to force fit a system to a space just because they're trying to make some money outside or something like that. That is unfortunately has happened. I've done audits that cover that as well. So this is the basic on space load calculation. The first one is overall rule of thumb. This is often like 60 BTU per square feet of area. This is not meant to be used for sizing of the equipment. So when do you use this overall rule of thumb? This is, let's say the owner has an idea. He say, I want to build a shopping complex of this many square feet. I just need an overall very high level budgetary estimate on what my system may look like in terms of just capacity. That's when you can kind of use this. So this is meant for very high level sanity check kind of exercise. It is not meant to be designed, but again, I've seen this being used for design as well. Oftentimes, like housing contractors, apartments, they'll probably use this. There's not really much losses for houses, but I have also seen it being used for office towers and whatnot. The second one is the detailed rule of thumb. It is a more detailed version. It uses some elements of detailed engineering. It uses some elements of rule of thumb, but it doesn't use the 60 BTU per square feet. I'll show you an example shortly. The purpose of this is more to have a feel and gauge on how each space is going to play out. So normally in detailed engineering design, we have something called a conceptual stage. We have 30% detailed design, 60%, 90%, and then we have something called the IFC, which is the issue for construction stage. So that is like the 100%. So the detailed rule of thumb, again, I've seen people use this for designing semiconductor plants, which is again wrong, but it has happened. I've commissioned systems that are based on this design. And the problem with using all this rule of thumb is you may end up not sizing things correctly in terms of the sensible and latent load, like what Faris mentioned earlier. Because if you don't take care of the latent load, you may end up with humidity issues. I've seen that happen in data centers as well. And humidity in data centers lead to increased corrosion. So that's a messed up one, because guys are using all this rule of thumb. So this rule of thumb is mainly meant for smaller spaces, maybe 1 or 2 stories office buildings, then you'll be fine to use this. But anything beyond that, especially when you're dealing with where the space use isn't just people sitting down doing work, we're talking about people, maybe eating or something like that. We have a lot of humidity. We shouldn't be using this. Next, we go to something known as CLTD, cooling load temperature differential. This is a slightly dated method. The last it was referenced even in S3 was probably 1987, but it is a good method. It is a manual method on how you will determine something called the load profile. So what is meant by a load profile? A load profile is how is your building's heat load going to play out by the hour throughout the day. So the CLTD will tell you that. In fact, it will even tell you how it will be based on each month. But it is not as complex as the final method, which is the transfer function method. which is often done using a software, because if you're going to do it on an Excel file, that thing is going to take you a long while, but that will tell you with precision detail how your load is being used in throughout the year, actually, that one. So the purpose of you having the other two methods in the end, you're able to optimize your size. You don't want to oversize your system. And on top of that, you will be able to know your load profile. Knowing your load profile, you'll be able to do certain things called like load staging, like how well you manage your load. Like for example, hotels may not always run at their full capacity. And if you only size your system with the mindset of running at the full capacity, systems may not run efficiently at their part load if it is not designed well to handle its designated part load. So that's something to keep in mind. So today's focus, because of short of time and because the other two methods like CLTD, I'll probably need half a day. The final method, probably a full day. In fact, the final method is also used in energy modeling. Like you're doing for green buildings, certain green buildings, they need to use energy modeling. You can use that. I've even used the last method, the transfer function method, in a legal proceeding, because somebody went and stole chill water from this guy from the owner of the plant for 5 years. And during COVID, they found out. And we even used that method in a court proceeding to claim the amount of use, how much of cooling have you used throughout the 5 years. So the last method is a very powerful method, but it's a thing that probably takes an entire day for me to teach you. So today's focus is the detailed rule of thumb. So this is how it will look like. As opposed earlier, let me just go back a bit. You see the overall rule of thumb is just one value. They kind of just lump it in, go by the square feet. The detailed rule of thumb, there's some load. Like say civil load here is the load you get from the walls or the windows, the amount of heat you're getting from it. So this we use around 80 watts per meter. By the way, if you're going to be getting involved in HVAC, get used to the concept of units changing from one to another, because some standards are written in the imperial unit, some standards are written in the standard SI unit. So it's a jumble. You need to be comfortable moving from one to another. So this, for example, is using 80 watts per meter for just the civil load. Lighting load, this is the number of lighting fixtures you have in your space. We often take it as a one-to-one. So for example, if your light is having a 10 watts electricity rating, their heat load will also equate to the 10 watts of heat. Like earlier Faris mentioned, when you're using the SI unit, the wattage, you need to be careful what kind of wattage we're talking. We're talking electrical or heat. Then we have the other loads like people heat load. In this case is 134 watts per person for office work. And then we have the last one is the electrical equipment load. This will also determine, like say your computer is 100 watts. A computer does not function the similar way as a light bulb would. So there's something called an emission factor. So these are based on the standards. For example, if you look up X-ray fundamentals, you'll be able to find the emission factor for a computer, what it may be. A rice cooker may be 0.7, a microwave probably also 0.7, something like that. So let me show you an example how, okay, before we go to the example, there's another thing we need to take into consideration when you're doing this rule of thumb. All this wattage you're calculating is what is known as the total cooling load or the total heat load. Total meaning it is a combination of sensible and latent. Like I said, if you mistakenly do not account for the latent, you may end up with humidity issues. So that's why it takes us to the next slide. This is what is known as SHR, which is the sensible heat ratio. It is the ratio of the sensible load over the total load. This value, this SHR ratio, is often used inside that cooling coil that is going to cool your space. Because the cooling coil will need to know, the manufacturer will need to size the cooling coil to know how much of sensible load I want to remove, how much of latent load I want to remove, because both are getting removed in that same coil. So how you want to size that coil, this is kind of like also a rule of thumb, but not necessarily correct. SHR ratio based on type of space and use. So for example, kitchens and cafeterias, you might notice it to be 0.6, 0.7. Why? Because there's a lot of food. Food is very moist, you got a lot of moisture there, you want it to be removed, or you may end up with mold issues. I've actually seen even hotels that did not consider that, people are going to be bringing food and eating, especially five-star hotels, big names with mold issues because they didn't design the system with latent load in mind. So their coil ratio was something more like 0.8, which was meant for, office space and stuff as office space. Can see it. Anyways, office is around 0.8. So they went and sized the coil ratio 0.8. It did not take into account the latent load. But again, this is rule of thumb. This is normally where your ballpark is going to be. So let me show you an example. Okay, let's say an office space of 80 meters square with 4 people working at seated. Space has 4 overhead lighting with each fitting rated at 10 watts, and each person has a laptop at 100 watts. So this is good, like I mentioned, for 30% to 50% detailed design. So it lets you to play around and understand the nature of the space. But later on, you'll probably need to do a detail engineering, especially if you're going to use some unique cooling systems, which we'll get to down the slides. So this is roughly how a typical calculation would play out. Okay, the room size, the civil load, that's your calculation. You just multiply the two, the number of lights, the watts fitting. Since it's a 1-to-1 for lighting, it's 60 watts. People load, you need to refer to the standard. What is the value? Because if the guy is, if it's a gym, then it's a totally different number because people are working out, there's more sweat, there's more moisture. And the last one is the emission factor. Since these are laptops, it's 0.3. And that's how you get your total heat load. Heat load and cooling load is interchangeable terms. And then I select the 0.8 sensible heat ratio because it's an office space. This is if you are using the rule of thumb approach. That's why you select this. The actual detailed part I will show you in the psychometric section of this webinar on how to actually calculate that without having to, rely on this rule of thumbs. So this kind of gives you the final summary of the space. Oh, my space is going to take up this much kilowatt of cooling, or in RT is 2.03. What is the load breakdown going to be like? So this kind of gives you the overall picture if you're using the detailed rule of thumb approach. Okay, now let's move into the psychometrics. So psychometrics is the understanding of the air and its properties. So oftentimes for people's comfort, we call it as thermal comfort, we often say the space needs to be 23 to 24 degrees C. The relative humidity is 50 to 60. I'll explain what these terms mean, RH and all that later. So this is what we have decided as to be the most comfortable situation where people don't really feel too uneasy. Previously, back in the day, people used to design it for 20 degrees C and then they put a jacket on. So this is basically telling you what would you feel with just ordinary clothes. This is the temperature that keeps people comfortable. And this part of the graph is known as the psychrometric chart, and this is where we consider as the comfort region. Let me go to the next slide. Okay, so this is the comfort region. Where's the mouse? Okay, there we go. You can actually even be, as a human being, you may feel comfortable in a 80 RH region where the relative humidity is quite high, but it may not be conducive for the surface or the the walls getting mold or even equipments. So we normally try to keep the RH level between 30 to 70. We don't want to go any lower because lower than 30, you run the risk of static. You get to have a lot of statics on the surfaces. That is why even data centers, they don't drop below 30. And if some of you have ever been to winter countries during winter, and you may feel that sometimes the hotel room doors are all very, you can easily get the static from it. It's because they are very dry and they're only heating. Later I'll tell you why that happens. So in common terms, you want to keep it within this range and you want to keep it within this bandwidth. So this particular area is where you want your kind of like your cooling system to cool down to. Okay, so the both are technically the same. This is using based on S355, the standard. This is based on the EN1525. It kind of gives it a bit more of a bandwidth. So that is that. Okay, so what is the psychometric chart? There's a few things here. The first one is the RH, it's the relative humidity. Think of it as moisture in the air, but there's also something else called the absolute humidity, or sometimes known as humidity ratio. So these two may confuse people because they're both, ratios of moisture to the air. But what's the difference? Absolute humidity or humidity ratio, which this is the weight of moisture or moist air with respect to the weight of dry air. RH is more of the how much space it requires, because the RH, because gas is expendable. I mean, the nature of gas, it can expand when it's hot, it contracts when it's cold. So RH is sometimes dependent on even the dry bulb temperature, which you see over here. Dry bulb temperature is just the temperature we normally feel. It's the degree C that we normally read. Wet bulb oil, you normally won't read it. So sometimes you see a thermometer or a thermostat on your remote, it's actually referring to the dry bulb temperature, which is this. And on the note of dry bulb temperature, removing and adding dry bulb temperature is actually removing or adding sensible load. You normally don't add unless you want to, maintain the RH, like I mentioned earlier. Latent load is, of course, removing the moisture. The very weight of the moisture itself is the latent load, removing and adding it in. Energy content is, like, say you got two particular points and you want to remove the energy, get the temperature from, like, say, this point to this point over here. The amount of energy or heat load removed is this enthalpy. I'll get to it shortly. Again, RH is a relative number. It isn't talking about moisture in the content itself. It can very well be a sequence of two variables, which is the dry bulb and the absolute humidity. So this is what I meant. This is your current condition. Let's say this is a outdoor system. You're just bringing cool fresh air. You want to cool it down right down to space condition. This is where you are, the current condition, outdoor temperature, around 36 degrees C. The RH is between 50 to 60, so it's around 55. We're planning to bring it all the way here to a cool 24 on the 50 mark, what we always like to have it at. So how do we go about getting it from there to here? This is all the type of cooling and humidification that can happen in a HVAC system. So as you can see, the pattern of movement with the mouse, the pattern of movement here. So you're doing what is known as a cooling and dehumidification. So earlier, remember the SHR, the ratio of coil that is doing sensible cooling and latent cooling. Latent cooling is basically dehumidification. So that is why it is important for you to bring down both, and you get this. So if you want to do something else, if you want to just do sensible cooling, there is times where you just do sensible cooling, especially in places where there are a lot more equipment and less humans, a very automated facility per se. You'll do what is known as sensible cooling. You don't really need dehumidification. So you don't really care about latent load, you'll just be caring about sensible load. Then you have sensible heating and dehumidification. This is often for heating markets, but again, some factories or processes, they use this as well. Cooling and humidification, this is a particularly interesting concept, which is called evaporative cooling. We'll get to that shortly. There's something called a dew point. A dew point is basically when water starts to condensate. 100% of the water condensates off. Right, let me go here. Yeah, so like I said, in a detailed calculation, you won't be referring to any table and determining, oh, what is my sensible coil ratio? You will be using this data right here. You will calculate your latent load based on this data. I'll show you the examples of formulas shortly. You will take the value here. Okay, what's my absolute humidity value here? What's my absolute humidity value here? You'll plug it into a formula, and that will tell you this is my latent load. And then you will do the same for your sensible load. You'll draw a line straight down. You'll check the dry bulb temperature here, dry bulb temperature here. You'll plug it into a separate formula, and you will know your sensible load. So now you know exactly my space, what is the ratio of humidity removal to direct cooling that I need. So this is the formulas. I've given it in two formats, the imperial units and the SI unit. This is kind of CMS is all the flow. So it is not just important that you have a coil running, you need to know how much air is flowing through it. So a combination of those two is how much of heat you're trying to remove from the space. So you just plug it in. This SI unit is a bit more complex because the imperial units came first, then only the SI units came in. So you need to know the air density. I've given you the values here. This is often used for space cooling. So unless you're using for process cooling, those values may differ because it might be going for sub-zero or whatnot. But for normally 24 degrees C, the air properties are pretty much in this ballpark. Temperature difference, outdoor, indoor. Example, not necessarily outdoor, indoor. When we are talking about recirculation, the pattern of movement doesn't go immediately down. If you're talking about systems that can do recirculation, there is some mixed air and all that. So it's like more like a triangle shaped thing we start to form. But that we will not go into it today. So this is kind of like the calculations. So if you're going like typical return air and supply air, and then you can calculate your loads based on that. Blah, blah, blah. Again, take note of the psychometric chart because like this chart over here, this particular chart is for SI unit, but there are certain charts that are in imperial unit. So make sure you're looking at the right thing. The easiest way to know is look at the dry bulb. Is it in degree C or degree F? And then just key in those values and you will know your units. So coming about heat load, this detailed calculation is what normally will happen in the last two approaches, and you will be doing it based on the hour because different hours have different heat exposure from the sun and different times that people come into work. You'll be doing this repeatedly for those detailed calculations, and that's how you'll know your flow profile. And it is also very important to decouple this in some of the specialized designs you're going to see. Like, for example, if you're going to use an active chill beam, if you're going to use a radiant cooling system, those systems are very good and very energy efficient at handling sensible load. But your latent load, you'll need to decouple it, take it aside, and you need to go put it into another system, which is called the DOAS. So that is more on load balancing. You'll need to do those kind of stuff. So now we go into global trends. This is just basics, like what is refrigerant? Okay, the refrigerant in the system, they all have something known as a GWP value, a global warming potential. So let's say 1 cubic volume of gas, if it's a CO2, if it's the refrigerant, some of these refrigerants are, for the same amount of volume, they may be 1,300 times worse than CO2 in terms of global warming. So in recent years, there's been a push, because previously people only cared about something known as ODP, ozone depletion potential. So that's why you have the banning of R22 that all can cause those ozone depleting problems, like those CFCs you see on the table. But now in recent years, they're also trying to reduce the GWP, the use of refrigerants with high GWP. That being like example R410A. So R410A has been widely used in the past couple of decades, past 2 decades, I would say, as a replacement for R22. A lot of systems are using R410A. It's been good, but R410A has a high GWP. In fact, in certain countries right now, they're already phasing out selling R410A, and they're moving towards banning it at some time, maybe in the next 5 or 10 years. So if you want to future-proof your systems, installations, look for installing systems that are not using R410A. Of course, they may still sell it because it's not yet outright banned in maybe our part of the world, but the trend is already moving towards that way. And if you want to future-proof your design, it is something for you to consider. Other than that, earlier what Faris showed was the FCU and AHU. That is what is known as the common systems for cooling the space. Then we have what is known as radiant cooling, which is cooling the space via radiation. But there's a caveat to radiant cooling. It only handles sensible load. You cannot handle latent load because, like I said, to remove latent load is removing moisture, meaning you literally condensate the thing out. That's why you see FCUs and AHUs, they have a drain pan that collects condensate water and then just throws it out somewhere. Whereas this guy doesn't do that. So you need to know how to decouple your load and use a DOAS to properly design the systems. Then you have induction cooling. Induction and displacement cooling are pretty much almost the same. Induction cooling can be the underfloor cooling. It's also very energy efficient. All these alternate systems are very energy efficient. Underfloor cooling is energy efficient in the sense that it uses a form of natural convection plus forced convection, because you're blowing the cool air from beneath, and we know from the movement of air, hot air goes up, cool air stays below. So because the air is coming from below, it's not very strong, it's just very mild, kind of naturally convects itself in cool space. So it's a good design. I've seen a couple of banks use it as well. The last one is active chill beams. It is a mixture of induction cooling and also a radiant cooling. So if you mix induction and radiant cooling, you would get what is known as active chill beam. Active chill beams, in fact, in Blue Snow, we did one design back in 2013. It was able to get LEED Platinum. A lot of people tend to say the systems are not feasible in Malaysia. Again, I don't see why it's not feasible when I know buildings that have it and can do it. Even the Prime Minister's office uses active chill beams. So the guys that say those systems are not feasible is probably afraid to design the system because you need to do proper detailed calculation. And oftentimes they normally take the shortcut of using the rule of thumb because they just want to save time and save money. Then we have alternative systems. This is on mainly water side. The use of district cooling plants. We see a lot of distraction of using district cooling plants for townships, especially in the Middle East. It's a very good thing to do because as building operators, sometimes their main concern is running a mall. They're not going to, be very concerned on how to run a cooling plant, and that's why you see sometimes those systems go bad. So by having a district cooling, it's kind of like you purchase chill water at a fixed rate. So it's actually very good because the district cooling plant can be maintained at a much better efficiency if they know how to stage those chillers and part load them well. The next is evaporative cooling. Evaporative cooling is using water and having air run through it and evaporating the water droplets into cooler air. But the caveat is evaporative cooling will increase humidity. That's a given. If you go later, I'll share the slides. You can actually go back to some of the psychometrics. You'll see that arrow that I showed here. Where is it? All right, here. Yeah, evaporative cooling does this. So why would somebody choose to increase humidity? I thought humidity is bad. In some instances, especially textile industries, they prefer to use it because the humidity for some reason gets reabsorbed because of their materials or the chemicals they use in the manufacturing floor. Mostly textile industries uses evaporative cooling. So that was something unique. And for us to design it, you need to properly understand because it's very correlated to the outdoor condition and also the movement of the air. Also very energy efficient because there's no chiller. There's no things that is consuming electricity except for the blower and a pump to pump water. So it's a very good system where you don't really need 24 degrees C, mainly for manufacturing areas. It's quite okay if your area is not too prone doesn't have a high sensitivity for humidity. Then you have a high delta T design. This is a chill water requirement. Normally chill water is designed for 6 degree supply and return temperature of the water, the delta difference. Having a high delta T is good because you can reduce your pump size, your pump consumption. So overall, you get a net positive in terms of energy consumption as a plant. All right, and that's concluding the short webinar. Yeah, thank you. This is us from Blue Snow. We are located in those active. These are mostly our active offices in the world. We do have a couple of others in Australia and whatnot, but those are not really that active at the moment. And back to you, Bennett. Are you still there, Bennett?
Okay, thank you. Thank you very much to the Blue Snow team. Certainly a lot of information packed into just over an hour. I'm sure there's a lot of questions from the audience as well. Given that we finished a bit early, I think we can extend the Q&A session slightly. Great to see we have got about 86 participants now. So the numbers have been increasing throughout the morning. So for those who did not catch the full presentation, maybe if you have some questions, you can put it down in the chat group, or you could raise your hand and voice it out as well. Maybe I'll just go through. There's one question that was put forward by Fakrul, right? Fakrul Roslan. I believe there's a conversation going on as well in the chat group. But the core question was, can you explain about centralized HVAC cooling systems? Is it the same as with water-cooled chiller systems?
Okay, I know where he's coming from because people often hear the word centralized, right? It's a common term is here in Malaysia. Oh, central system. It can mean many things. It either can mean the VRF. Oftentimes, it's the VRF versus the chill water systems, meaning that all of the indoor systems is connected to a central outdoor system. So that is why the term central cooling comes in. So it can actually even be both. Sometimes you say, oh, I'm using central system, but you go and check it. Really, it could be a VRF system. It's basically meaning all your indoor system is connected to a centralized outdoor system. In the case of water cooled systems, it's a chiller that is connected to. It's a central point. It's a one point of contact. Whereas in a refrigerant system, the VRF would be there. So that's why that terminology comes often used in typical building management guys that say, "Oh, I have a central system." That's what it means. It basically means all your indoor system is connected to a one endpoint, so to speak.
Okay, great. Yeah, so centralized is a more generic term, can apply
Yeah.
to package units, water-cooled chillers, etc. I guess, would you like to elaborate? I mean, sorry, do you want to get further clarification on that, Fakrul? Or is that okay?
I think so far from the explanation through chat and also your explanation here, so I think more or less I got the understanding on the centralized HVAC system. But maybe I got some other things to ask, and maybe later after the session.
Okay, sure. Yeah, thanks, Fakrul. Yeah, a few other housekeeping questions that were asked. So the video, the session is recorded. We will make it available on an upcoming YouTube channel, which the CAMGBC is setting up. It's still a very new organization. So do like the Facebook page. There's a LinkedIn page, Facebook, and a YouTube channel that's upcoming. So all the upcoming webinars, notifications, etc., will be shared via that platform, and all recordings of webinars as well. I believe Naveen had put up a little brochure of an upcoming paid seminar, but this will be held physically in Cambodia and Phnom Penh at Northern University on the 4th of April 2025. So for those in Cambodia, if you're keen, there's a special rate for members as well. Do join in for a more detailed, in-depth sort of run through the topic on hand. Okay, is there any other technical questions? Anyone? All are experts already, I think. Okay, I have one question, if that's okay.
Go ahead, Rashid.
Earlier, Naveen mentioned that VRF systems are very common in Cambodia. High-rise buildings there are not, you don't find chill water-based systems very often. Of course, one of the drawbacks, as you pointed out, was the efficiency cannot possibly match the levels of a chill water system. Is there another drawback that we could possibly quantify? You're running a lot of refrigerants across hundreds of meters.
Yep,
Is there
definitely.
a rule of thumb on the loss of refrigerant, maybe per meter per year, that we can
Okay.
quantify and also put it down from a greenhouse gas emissions perspective as a negative? And what are the solutions to mitigate them as well?
Okay, the first thing is that one we normally talk about what we call as a refrigerant impact assessment. So normally the rate of losses we would estimate is 0.5% or maybe was it 2 to 0.5% depending on workmanship of loss of refrigerant based on the amount put into the system. So let's talk about what you mentioned, the VRF. So when the guys want to charge this refrigerant, they call it charging the refrigerant. They'll have these barrels of refrigerant that come in, and they will try to connect it, and then they'll just keep feeding it in. So there's weight of the refrigerants are all inside the system. And depending on workmanship, there may be leakages and small hairpin ones that you may not feel it over time. And the leakage rate is around 0.2 to, 0.1, 0.5% to 2% of the total volume that's inside your system may leak annually. So that's why sometimes you see even your aircon in your house, the guy comes in and tops up the refrigerant. By right, under good workmanship, you don't need to top up a refrigerant. Because like chillers, they very rarely get topped up. They are the same refrigerant inside the loop, but they are done in a much more precise and well-engineered manner. But you're right, in large buildings, using refrigerant, you have refrigerant pipes running all over the place. And the amount that you actually use, if you're going to go for per contrast, you may end up actually using more refrigerant there. And using those refrigerants like the R410A and this leaking into the atmosphere, it's going to have a much more impactful, negative impact on the environment, especially when talking about greenhouse gas. So you may be doing things like recycling and whatnot, sending your recycling bin to the recycling center instead of the landfill. But having these refrigerants, like I mentioned, they are sometimes 1,300 times worse than CO2. Leaking into the air is going to be a much more worse scenario to go in. So that is why for this entire seminar here was to introduce chill water systems to the Cambodian market and get them more comfortable and understanding and the benefits of it from not just the energy efficiency standpoint, but also from the carbon emission and the carbon impact standpoint. So I hope I answered enough, Ashwin.
No, but Ashwin, I would like to add, to what Naveen mentioned. I think something Naveen mentioned during his presentation earlier was the life of this VRV systems. People expect that once they install a VRV system, it's there for life, as it lasts as long as a chiller system. And it's not true, because we understand something. In all your compressors, there's oil, right? And this oil mixes with the gaseous refrigerant in the compressor when it's hot. So when it pumps out that to the the condenser and goes back to the evaporator, if you remember what Faris showed earlier, some of this oil also gets into the evaporator. And in this term, when I use the word evaporator, it means the indoor unit. Over time, when that droplets of oil builds up in your evaporator, it retards your heat transfer space in that. And ultimately, you'll find that your two things happen. One, you're not getting the right cooling. When in the first year it was very cold, then you start dropping the temperature. You think by pushing it down to 18, you get much better cooling. That doesn't happen. And number two, because the oil is now covering the tubes, remember Faris mentioned that the liquid refrigerant has to evaporate. Now, if it doesn't evaporate, it stays as liquid. And liquid can also get back to the compressor. And compressors cannot compress liquids. So compressor will fail. So that's why, as Naveen mentioned, 6-7 years after that, you got to change. And this is not what he's mentioning is not what we feel is actually happening to a lot of our clients who have also moved away from VRV systems to central chill water plants just because of that.
Okay, excellent. Yeah, thanks for that, Bernard and Naveen. Yeah, indeed, a lot to unpack there. A lot of optimizations that we can do to air conditioning systems to improve their efficiency. As the UN has projected, at least in Malaysia, April is going to be one of the hottest months on record ever. So the need and that trend is probably going to continue in the coming years. So the need for efficient air conditioning systems is increasing in importance year on year. I'm sure most tropical countries will feel the same sort of run, Phnom Penh as well, and we've got attendees here from even Saudi Arabia and all that. So air conditioning is going to need to be optimized very, very much so going forward. Okay. With that, any other further questions from the audience? Only one question so far. Okay, I guess, Bernard, you've shared your contact details as well. We will be sharing the slides to all those who have registered, and I believe those who didn't have the opportunity to register have shared their email addresses also. So we will share the slides, share the contact details. You can always post your questions directly to Blue Snow as well, going forward.
Sorry,
So,
Ashwin, I saw a question, I think in the chat, somebody asked about this particular seminar, whether, although it's physical in Phnom Penh, could they dial in and into the seminar? I think something that maybe CamGBC should look
okay.
into as well.
Okay, yep, sure. Something we can explore, maybe a hybrid sort of attendance option. Yep, sure. We can look into that. Also, I think those from Malaysia joining via Green RE, the CPD points, you'll be eligible for CPD points as part of this webinar. So I do share your details and Narima will get in touch. With that, okay, if there's no further questions, can we take a quick photo of the webinar? Maybe Aline, could we do a quick photo session? We've got more than 80 participants. Great start to our webinar series by CamGBC. Maybe those who can put your cameras on, please do. But those who can't, maybe, you don't, a bit shy, it's no problem. Just have yourselves with your name listed on the screenshot.
As long
How
as
do we do this?
those you guys are not in your shower. Yeah.
Maybe Aline, could you tell us if it's all okay? Yeah, I think everyone's got their cameras on. Excellent.
Okay, wait, we are setting.
Setting up, okay. You got to do it in sections. Narima, you are muted. Yeah.
Ready? One, ready? 1, 2, 3.
Narima, you're muted. Is it okay?
Yeah. We have four pages, so we need to capture one by one. Okay. The
Okay,
first
so
one I
first
think
page
is
done?
yeah,
First
first
page
page
done. Okay.
done. Yeah.
Second page.
Okay, 1, 2, 3.
Okay. Third page now. Okay.
One, two, three.
One more page. Okay, is that all done now?
Yeah, done.
Okay, excellent. So thank you everyone and look forward to seeing you in the upcoming webinars and events. Thank you.
Thank you.
Thank you.
Okay.
Thank you.
Bye.
Thank you.
Một tin tin thanh hồn nha lo. Bố yakin xiao ing mà để rồi bố nó buồn học với này kinh chồng lắm kinh hiệp xiao ing này thanh hồn nha mà